Here we have another in a long line of classic optimization problems, probably found in all Calc 1 classes. This time we're trying to find a point on this curve, which is the curve y equals x squared, kind of drawn sort of sketchily here. There's a point somewhere here that is going to be closest to the point 2 comma 1/2. So what we need to do is get a formula for that distance between those two and then try to optimize it. In other words, try to find a minimum value of that distance. And we'll do that by getting a formula for the distance, and then we're going to take its derivative, set it equal to 0, determine the critical values, and then determine if we did indeed find a min for the distance. So the first thing I'm going to do is maybe draw that distance, I guess in green, and I'm just going to kind of shoot a line over there and say, okay, that's the distance that I'm trying to minimize. And the way we're going to kind of find that distance is represent this point that we're heading toward as a random point xy that's on that curve. So that point we've come over x and up y. So if we want to find that distance, we think about the distance formula whether you remember it or not, but it's basically just Pythag. So we could drop a perp down here and come over that way, and we'd realize that regardless of where that point is, where that xy point is, whether it's here or here, we could drop a perp and come over and get a right triangle. And now what we need to do is, in order to get a formula for D, kind of come up with expressions for this vertical piece and this horizontal piece. So remembering that in order to get to this point, we came over x units, and this point is over at 2 units. So you can imagine, for example, take the case where x is 1. This distance would be 1 because 2 minus the distance that's here, which is 1, would leave you with 1. Since this distance, which maybe I can show as, I'll show it in red, this distance is x, that leaves this distance as 2 minus x. Similarly, we have the vertical piece right here, where the whole thing is, all the way up to there is y, and this part is 1/2. So what's left is y minus 1/2. That's that part right there. So thinking of this triangle, maybe blowing it up a little bit, we could have something like this, where the base is 2 minus x, and the height is y minus 1/2, and this is D. So we've just kind of highlighted this triangle here and kind of blew it up a little bit so we have a better picture of what's going on. If you don't follow where these values came from, I'd suggest plugging in some values for x and y and kind of testing it to kind of convince yourself that those expressions y minus 1/2 and 2 minus x are going to work to get you what we need to do. So a relationship that we'd have now, kind of as a result of that, is we'd have d squared is equal to 2 minus x quantity squared plus y minus 1/2 quantity squared. So it's basically a squared plus b squared equals c squared. Before we plow ahead on this, though, probably want to realize that just in like many of the other problems that we've looked at in this section, we want to have one variable here, and we have y and x. And nowhere in this formula have we taken into account what y is equal to. The fact that it's equal to x squared is going to be kind of huge. So let's quickly rewrite this as 2 minus x quantity squared plus, instead of y here, we're going to use x squared minus 1/2 quantity squared. And that's what d squared is. Now, we could, if we wanted to, solve for d, which would be the square root of all this stuff, and then find d prime and do our thing. However, we talked a little bit in class about, in order to make a distance small, it's sufficient to make the square of that distance small. In other words, if you find a small value, you get this square of this thing to be as small as possible, I guarantee you the value that makes this small will make d small, because you're just taking the square root of it. So the square root of a small number is going to be a small number. So what we can do in all these problems is, maybe I'll just, since we want to find the minimum distance, maybe I'll call this d squared function, maybe I'll just call it something else like m. The other thing I'm going to do is maybe FOIL these guys out so that we have what will look like a polynomial. Well, it will be a polynomial. So foiling 2 minus x quantity squared is going to be 4 minus 4x plus x squared. And then foiling this guy out is going to be x to the 4th. and then we're going to get minus 1x squared, and then we're going to get plus 1/4. If we want to go ahead and gather some like terms there, we could say that function is x to the fourth. Got him taken care of. Now this x squared and this minus x squared sort of kill each other. So our next term is going to be negative 4x. And then lastly, we've got him taken care of. We've got a 4 1/4, which is like 17/4. Not really going to matter though, because as soon as we take the derivative of this thing, that constant's going to go away. So the derivative is going to be 4x cubed minus 4. So if we set that guy equal to 0, we're going to get our critical numbers. So first thing I would do is divide both sides, divide everything by 4, and we get x cubed minus 1 equals 0. And that means that x cubed equals 1, so that implies that x is equal to 1, taking cube roots of both sides. So it'd be nice to know that that x equals 1 represents a minimum. So I'm going to do the second derivative test. I'm going to go m double prime, which is 12x squared. And of course, m double prime evaluated at 1 would be 12 times 1 squared, which of course is greater than 0. So that means our function is concave up because we have a second derivative that's positive, and yet the slope is 0, so that represents a minimum. X equals 1 is a minimum, and of course we're trying to find the coordinates of the point, so it looks like that point right there is going to be when x is 1, and of course if x is 1, 1 squared is 1, so the y value is going to be 1. So that point is actually 1, 1, really rigged nicely with some good numbers to make sure that our distance wasn't too crazy to find. So there you go, another classic optimization problem, a point that is closest to a point on a curve.